Chapter 7, Section 2, Arithmetic and Geometric Series. In the previous lesson, we studied arithmetic and geometric sequences as a list of numbers in a specific order. Now, in this section, we're studying a series. A series is simply the sum of numbers in a sequence. So basically, you're adding the terms in the sequence. So instead of in a sequence, each term is separated by a comma. Here, in a series, each term is separated by an addition sign. Now, what we want to do is introduce special notation called sigma notation. This is an example of sigma notation. This letter is the capital Greek letter named sigma, and it is used to denote a sum in mathematics. So here, this is sigma notation. This is saying that you want to add this expression, n squared, and you're going to let n go from 1 all the way through 8. So you're going to plug in n equal to 1. This is called your index of summation. N equal to 1 is called your index of summation. And it tells you what number you're going to start plugging in first. So you're going to start with the number 1. It doesn't always have to start with the number 1, by the way, but in sigma notation, it always tells you what number to start plugging in, and then the number up top is which is an 8, is going to tell you what number to end with. Now, so you're going to plug in the number 1, 2, 3, 4, 5, 6, 7, 8, all the way through 8, and you're going to add all this up. So this sigma notation would be equal to the following: 1 squared plus 2 squared plus 3 squared plus 4 squared all the way through 8 squared. All right? So notice I started with the number 1. I went all the way through 8. Now, these are not commas. These are plus signs, okay? So then this gives us 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus 49 plus 64. Now this, everybody, is an example of a series. This is a series because this is a sum of terms, a sum of numbers. Now what we want to do is figure out the sum of this series, right? That's what the instructions say. So you're going to see me add all of this up now and find the sum, which is 204. So 204 is the answer. All right, everybody? So this is sigma notation, and this is a series. Sigma notation determines a series, and we can find a sum. Here's a brand new one. Determine the sum that is represented by the following. I kind of want to add to the instructions. I would like to say determine the series and the sum, all right? Because that's what we're going to end up doing anyway. All right, this sigma notation, the letter sigma says you want to add this expression 3 times n as n goes from 5 to 10. So your starting input value would be 5, and you want to go through 5 all the way to 10. So this is what we would get, everybody. We would start with 3 times 5 first, plus 3 times 6, then 3 times 7, all the way through 3 times 10. This is generating the series. All right, let's keep going. All right, this gives us 15 plus 18 plus 21 plus 24 plus 27 plus 30. Now, guys, this here, I just want to emphasize, this is your series. This is a sum of numbers. So this is a series. All right, the sum is 135. So this is sigma notation, everybody. This is really exciting. What I want you to notice is that sigma notation, this notation right here, represents all of this series. All 15 plus 18 plus 21 plus 24 plus 27 plus 30, all of that is represented in this notation. So really, sigma notation is really shorthand for writing out a series. Now watch this. The table has been turned around, everybody. They have given you this infinite sum, which is an infinite series, really. And they want to know what the sigma notation is for this. What's the shorthand notation? So first of all, let's notice the pattern, okay? It starts with the number 2, and then it goes to 4, and then it goes to 8, 16. What's the pattern here? That's the key, is identifying the pattern. So I'm noticing that these numbers are all powers of 2. Like 2 is the first power of 2, 4 is the second power of 2, 8 is the third power of 2, 16 is the fourth power of 2, and 32 is the fifth power of 2. In other words, the pattern is 2 to the first power plus 2 squared. Do you see that? Plus 2 cubed plus 2 to the fourth plus 2 to the fifth plus etc. Sometimes the pattern is relatively easy to find or easily seen. Other times it's really harder. It's a lot harder to see. So it all depends on the series that they give you. Now, what should we do? We have to write this using sigma notation, all right? So let me put some equal signs. So that's equal to that, which is equal to, all right, here's my sigma. Now, I need to tell the reader what we're adding. And so what we're adding is 2 to the nth power, right? 2 to the nth power. And I should have the readers know that we are starting with plugging in 1, and this is an infinite sum. You see this etc. here, etc., etc., etc. That means, and they even wrote it in the directions, it's infinite, so never ever stop. What does that mean? That means up here is the infinity symbol. So keep on going forever. This is sigma notation for this sum. All right, so this is your answer. Cool? Sometimes we want to take a finite, meaning there's a certain number of terms, finite arithmetic series, and add up a certain number of terms. And so this here is the formula for finding what we call a partial sum. Capital S just means a partial sum, and n, the subscript n, tells you how many terms in the series you want to add. And so here's the formula for finding the sum or partial sum of n terms in an arithmetic series. N here represents how many terms you're trying to add, which is given to you by the subscript. A sub 1 stands for the first term in the arithmetic series. A sub n stands for the nth term in the arithmetic series. Okay, so let's see if we can use it. And this is an example, our next example. We want to determine the sum of the first 40 terms. How many terms are we adding? 40. So in this case, 40 is n, the number of terms that you want to add. Of the arithmetic sequence with general term a sub n is equal to 5n minus 11. Okay, so in order to figure out the sum of the first 40 terms, you know, the long way to do this is to start listing out what the first 40 terms are and using the general term, and then start adding all those numbers. But that would take a really, really long time. The partial sum formula here would have us cut down that time tremendously, all right? So all we need to do is find how many terms we're adding, that's given to us, figure out what the first term is, and figure out what the 40th term is. All right, so n is 40, right? Because they said add the first 40 terms. Now, a sub 1, the first term in this arithmetic sequence, is going to be found by 5 times 1 minus 11. We did this kind of work in a previous lesson. So this is 5 minus 11, which is negative 6. So there's my first term. Now I need to find my 40th term. So it's 5 times 40. Do you all see what I'm using? I'm using the general term to find the first term and the 40th term. Minus 11. So this would be, what is this, 200 minus 11, so 189 is the 40th term. So I have everything I need to calculate the sum of the first 40 terms. I'm going to use this formula right here, everybody, and I have to move the screen up. So I'll move the screen up, but I'll rewrite the formula for us, okay? So here it is. Here's our formula. And so the sum of the first 40 terms of the sequence is equal to 40 divided by 2 times -6 plus 189. Look how cool this formula is. I mean, I don't know if we really can appreciate it unless you are asked to do this the long way. And again, the long way is to list out all 40 of those terms and then start adding them one at a time. That'd be crazy. All right, so then this would be 20 times 183, which gives us 3,660. This right here is the sum of the first 40 terms of this sequence right here that has this general term. Isn't that pretty great? All because of the partial sum formula. Awesome. Check out this question. Determine the sum of the first 25 terms of the sequence 9, 5, 1, -3, -7. Now guys, if they want me to add the first 25 terms of the sequence, I want to use this formula for the partial sum for an arithmetic sequence. Now the problem I'm having right now is I have to first confirm that this is an arithmetic sequence, because if it's not an arithmetic sequence, I'm not allowed to use this formula. This partial sum formula is only applicable to arithmetic sequences. So let's confirm really quickly that this is arithmetic. How do we do that again? Well, we did that in a previous lesson. All we have to do is find the difference between every pair of successive terms and show that the difference is the same. All right, so what I'm going to do is I'm going to take the second term and subtract the first term to show what that difference is. 5 minus 9, okay, that's -4. Let's check the difference of the third and second term. So 1 minus 5, -4. It's looking good, you guys. The fourth term minus the third term. So then this is -3 minus 1, -4. Still looking good. One more to check. A sub 5 minus a sub 4, which is equal to -7 minus -3. So this is definitely -4 as well, because it's -7 plus 3. So because all of these differences are the same, it's a common difference, we know for sure this sequence that they gave us is arithmetic. Because it's arithmetic, I'm able to use this formula to calculate the sum of the first 25 terms. Okay, let's use it now. What do I need? I need n, a sub 1, and a sub n. We know n is 25 because they want us to add the first 25 terms. Good. We know the first term, it's given, it's 9. What we don't know is the 25th term. A sub n is the 25th term. Remember, you guys, however many terms you're trying to add, that's your n value. So a sub 25 stands for the 25th term, which I do not know. Now, do you remember the general term for an arithmetic sequence? I asked you to highlight it in your notes to keep it handy because we're going to use it. The general term for an arithmetic sequence is a sub n is equal to a sub 1 plus n minus 1 times d. So if you're looking for the 25th term, n is 25, right? N is 25. The first term is 9 plus n is 25. And we already calculated the common difference. Do you remember what it was? -4, right? So let's figure out what this is. Let's do this arithmetic. This is 24 times -4. So then this is 9 minus 96. So then the 25th term is negative 87, I believe. All right, cool. Now we know what the 25th term is. I have everything I need to use my formula. This one that's still barely on the screen here. Let's use it. Okay, so here we go, ladies and gentlemen. Let's find the sum of the first 25 terms. S sub 25 is equal to 25 over 2 times a sub 1, which is 9, plus negative 87, which is the 25th term. Cool. Let's do this arithmetic, and then we'll be done. So then this is equal to 25 halves, I'll leave it as improper for now, times negative 78. Okay, and then we can cross cancel. 2 goes into 78. What's half of 78? Well, half of 70 would be 35. So then this would be 39, negative 39, right? So then this is 25 times negative 39, which is negative 975. We did it. The sum of the first 25 terms is negative 975. And I did not have to list out all 25 terms and then add them. That would be a pain. So this formula is really great. Check this out. Find the following sum. 12 plus 15 plus 18 plus 21 plus blah, 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 plus 270. All right, you guys, right away, when they ask me to find a sum like this, I want to use this formula. This is the formula for a partial sum of an arithmetic sequence, right? But before I can use this formula, I need to verify that the series that I have, or the sequence that I have, is arithmetic. So I have to confirm that by finding the common difference. So let's do that now. All right, we've done this already a few times in our lessons, so we can show that there's a common difference. So this for sure is arithmetic. All right, so we can use our formula, okay? Now, we know what the first term is. It's 12. And we know what the last term is. The nth term is 270. What you and I do not know is how many terms are there. Because of this etc., I don't know how many terms I'm adding. It just says find the sum. So we need to find n. Now we can do this by using the general term for an arithmetic sequence. All right. What we can do is we can plug in 12 for a sub 1. We can plug in 3, which was the common difference, wasn't it, that we found earlier, for d. All right. So then this leads us to 12 plus 3n minus 3. Let me move this down further. And then this leads us to a sub n is equal to 3n plus 9. Now what we can do is we know that the last term is 270. So I can plug in 270 for a sub n and then just solve for n. N is our unknown, okay? Remember that a sub n stands for the nth term, or in this case, the last term, all right? So subtract 9 from both sides. And that leads us to 261 is equal to 3n. And then now divide both sides by 3. And you get n is equal to, okay, got it. You get n is equal to, 3 goes into 26, 8 times, that's 24, and then you have 21, so 87. So that means the series that they gave us in the very beginning has 87 terms. So this was the last piece that I needed in order to figure out the sum of our terms. So we got S sub 87 is what you and I are finding, the sum of 87 terms, right? Here's the formula, over 2 times, times a sub 1, which they gave us to be 12, plus, and then the last term, the 87th term, is 270, like that. All right, let me move this up a little bit here. So then this is equal to 87 halves. You can change that to a decimal if you like, times 270. 82. And then I like to cross cancel. So 2 goes into 282, 141 times. So then the sum of the 87 terms will be 87 times 141, which is 12,267. This is the sum of those 87 terms. Pretty cool. Now, the last part of this lesson will be us calculating a partial sum for a geometric series. Now, here's the formula for calculating that sum here. Now, again, a sub 1 stands for the first term of your geometric series. R is your common ratio, and N stands for, see, N is here, a subscript, and it's over here on the power of R, as a power of R, stands for how many terms you're adding. Check this out, guys. Determine the sum of the first 10 terms of this sequence. Now, if you did a check, this would not be arithmetic. Now, you can prove it, right, by just checking the difference between each successive pair of successive terms. Here, I can show it to you really quickly. 6 minus 2 is 4. So the difference between these two terms is 4. But the difference between 18 and 6 is 12. So right there, I can see this is not arithmetic. But it is geometric. Now, I can prove that it's geometric. And I do need to prove that it is geometric before I can use the formula for calculating the sum of n terms of a geometric series, right? So here we go. This is what we did in a previous lesson. We took a pair of successive terms and we found the ratio. So 6 over 2, for example, would be 3. And you have to confirm that it's the same for each pair. So the third term and the second term would be 18 over 6, which is 3. Let's do it again. Fourth term over the third term. Do you remember doing this in the previous lesson? This would be 54 over 18, which is 3. So what I want you to really zero in on here is that it's a common ratio. Because it's a common ratio, I know for sure this is geometric. And because it's geometric, I'm allowed to use the formula. Now, in order to use the formula, I need to know how many terms I'm adding. Well, they gave that to me. They said find the sum of the first 10 terms. And I need to know what the first term is. Well, I know what that is. It's 2. Okay? I need to know what the common ratio is. We just figured that out to be 3. So I think we're ready to calculate the sum of the first 10 terms. So it's S sub 10 is equal to the first term, which is 2, times 1 minus 3 raised to the power of n, which is 10, and then all of this divided by 1 minus r, which is 1 minus 3. So the rest of this is just arithmetic, okay? So then this is 2 times, now down here we have negative 2, right? So you can confirm this number, negative 59,048. All I did was I punched 3 to the power 10 into my calculator, and I subtracted that from 1. Some of you might want to punch in the number 1 first on your calculator, and then minus 3 to the 10th power to confirm this number. Hey, look what we can do. This 2 divides into that 2, and then those two negatives here also cancel, and so your sum is 59,048. Cool. We found the sum of the first 10 terms for this sequence, for a geometric sequence. Check this out. We're almost done. Determine the sum 3 plus 6 plus 12 plus 24 plus blah, blah, blah plus 6,144. Okay, so with a quick test, you can show that this is geometric. If I take the second term divided by the first, I will get 6 over 3. The ratio is 2. If I take the third term divided by the second, I will get 12 over 6, which is also 2. If I take the fourth term and divide it by the third and find that ratio, I will get 24 over 12, which is 2. So then I'm seeing that there's a common ratio, 2. Okay? So I know that this is geometric. Because it's geometric, I'm allowed to use the formula for finding the partial sum, which is given here. Now, I know that my first term is 3. I know that my R value is 2. We just figured that out. What I don't know is N. N stands for how many terms there are. How many terms are you adding? They never said find the sum of the first 15 terms or find the sum of the first 20 terms or whatever. They just said find the sum. And I don't know how many terms there are, right? So let's find N. I think we can use the general term for a geometric sequence in order to find N. Do you remember this? This is the general term for a geometric sequence. Now, we know the first term is 3. We know that your common ratio is 2. Pretty cool? So what I want to do now is plug in, remember a sub n stands for the last term or the nth term, and the last term is 6,144. So I'm going to plug that in for a sub n and then solve for n. All right, 6,144, and then I have 3 times 2 to the power n minus 1. I can divide both sides by 3. So this is similar to what we did in another example. This would give us 2,048 over here is equal to 2 to the power n minus 1. Now, at this point, you can use logarithms to solve for n, or you can realize that the left-hand side is actually a power of 2. All right, with these values known, I can now find the sum of the first 12 terms here. And so it is, I'm using the formula, 3 times 1 minus r to the 12th, oops, sorry, r is 2. So 2 to the 12th power. All of this over 1 minus r, which is 1 minus 2. Cool? So the rest of this is arithmetic. So then this is equal to 3, and this is over negative 1. And then this number here, you want to punch it into the calculator, 2 to the power 12, and subtract that from 1, which should be giving us, negative 4,095, like that. The two negatives cancel, right? And then when you have a denominator of 1, then it's unnecessary to write it. So it's just 4,095 times 3, which is 12,285 using my calculator. So this is the sum of those terms. Isn't that great, everybody? Now, to wrap this up, I just want you to notice that every time we were finding a sum, we had a specific number of terms they wanted us to add, whether it was adding 8 terms or 20 terms or the sum of the first 10 terms or whatever. It's always been a finite number of terms that we're adding. So then how do you calculate the sum of an infinite geometric series? So you have a geometric series that continues and it goes indefinitely. How do you calculate the sum of a series that never stops? Well, I'm glad you're asking. So here's the formula for calculating the sum of an infinite geometric series. So here's the formula. It's actually a lot simpler than the partial sum formula of a geometric series. Here, a sub 1 is the first term and r is your common ratio. Now this is very important. In order for this to work out, that is to say, in order for the sum to be defined, the absolute value of your common ratio must be less than 1. If it is not, then that means the sum cannot be found. So check this out. Determine the infinite sum. Just that idea alone is pretty fascinating. Determine the infinite sum of 1 plus 2 plus 4 plus 8 plus 16 plus etc. forever. Now, in order to use this formula, we have to confirm that this is a geometric series. So let's do that. You're probably an expert at doing that now. Let's find the ratio. A sub 2 over A sub 1 would be 2 over 1, which is 2. A sub 3 over A sub 2, the third term over the second term, would be 4 over 2, which is 2. A sub 4 over A sub 3, that is the fourth term, over the third term, would be 8 over 4, which is 2. You can show this one more time. The fifth term over the fourth term would be 16 over 8, which is 2. What you just proved, what you and I just proved, is that there's a common ratio of 2, which proves that this is a geometric series. Cool? Now, we know that r is 2. In order for the sum to be defined, the absolute value of r must be less than 2. However, the absolute value of r, which is the absolute value of 2 in this example, is 2, and this is not, it's not less than 1. Therefore, this sum is undefined. We can say it like this. This geometric series does not have a finite sum. Last example. So I don't know if that makes you happy or sad. It makes me sad, but determine the infinite sum 3 plus 2 plus 4/3 plus 8/9. Now, I probably sound like a broken record, but it's okay. I want to use this formula, but I can only use this partial sum formula if this happens to be geometric. So let's prove that it's geometric. Let's take the second term and put it over the first term. I'm finding the ratio between these two terms. So it'll be 2 over 3. The third term over the second term would be 4/3 over 2, which is 4/3 times 1/2, right? Which is 2/3. Let's go for the fourth term over, fourth term over the third term. So then we have 8/9 over 4/3, which is 8/9 times the reciprocal, which is 3/4, which happens to be, if you cross cancel, 2/3. So you and I just proved that there is a common ratio, and that common ratio is 2/3. So this series is geometric. I'm allowed to use this formula. Now, we just found that r is 2/3, so that's good. The only other number I need is a sub 1, which is given. The first term is 3. You know, one thing you have to confirm, everybody? You have to confirm that the absolute value of your ratio is less than 1. In the previous example, the absolute value of our ratio was 2, and which was larger than 1, so we said there is no finite sum. So let's make sure the absolute value of our ratio, common ratio, is the absolute value of 2/3, which is 2/3, which is indeed less than 1, so the sum exists. All right, we're ready to use this formula, which seems like a very simple formula, right? Now let me, here, I think I could squeeze it in down here. We're finding an infinite sum, all right, everybody, because this series goes on forever. So it's equal to the first term, which is 3, over 1 minus the ratio. Cool? So it's arithmetic at this point. Let me just move up all the way here. All right, cool. So then this is equal to 3 over. Now remember, that 1 minus 2/3, you know what? I'm going to do it this way, all right? I just changed my mind. Give me a second. What you can do is there's a few different ways for you to simplify a complex fraction. What you can do is multiply every single term by the LCD. Now, the only denominator I see is 3, so my LCD is 3. So what I can do is I can multiply this by 3, this term by 3, and this term by 3, right? And of course here, this 3 and that 3 divide out. So I don't know if this is better for you, but it would give you 9 over 3, right? I got the 9 from 3 times 3. I got this 3 from 3 times 1. And then it'll be minus 2. I'm not sure if you like simplifying like that better. Minus 2. All right? So then this turns out to be 9 over 1, which is 9. Isn't that amazing? You know that infinite series that we saw in the beginning right here? Actually, I think I can, yeah, here it is. If we add this and keep on adding forever, the infinite sum will be 9. That is pretty fascinating to me. All right, everybody, this is the end of this lesson, and it's also the end of us studying sequences and series. We could take it a lot further, but this was just an introduction, these two lessons together. All right, I hope you had fun.